Thank you so much for coming today. I'm going to present the results of my master thesis. This work was supervised by Professor Eric Miller and is related with prediction of salaries in the Greater Toronto area. So the outline of this presentation, first I'm going to start with what motivates me to do this work, and then I'm going to present the components of the labor market and how these components are integrated into the UT framework. Then I'm going to present the model that we built, the specification of that model. After that, I'm going to present the results, both at the aggregate and disaggregated level. And finally, I'm going to present some conclusions and conclusions. So, when we talk about labor markets in transportation, transport models have grown in complexity, but some inputs still remain exogenous. And this is more important because work is the second most frequent trip purpose in the GTA area, according to the TTS survey. Also, some variables such as place of residence, place of work, household income, and auto ownership are directly or indirectly related with the outcomes in the labor market. So for that reason, we consider that we need to integrate that part into the transport models. But how we integrate the labor markets? First, labor markets are usually have two components, two agents, one on the supply side, there are the individuals. On the demand side, we have the firms. And both agents make decisions, both in the short term and in the long term, and both agents enter the market to agree into main parts. First, the wages and the working hours. So we can see here that wages are an important component of this process, because wages facilitate the interaction between the agents, but also wages allocate the labor to the most efficient use by industry, by occupation, or by regions. Labor markets also have a particularity, that is they are organized in a hierarchical structure in which one job belongs to an occupation and that occupation belongs to an industry. That structure defines many attributes, both on the firms, on the individuals, but also contributes to have the wage differentials. So we consider that this structure is really important to be included if we want to model labor markets. So this work is built upon previous work by two students of Professor Eric Miller. The first one, Michael Hain, in 2010, proposed one hourly wage model that is a linear regression based on some attributes of the worker, and a series of logistic regression models to assess the job transition. In 2013, Adam Harmon took those models and built an agent-based simulation in which he modeled three processes. The first one is the worker state update, the second is the job creation and deletion, and the third one is the job search and matching. This is one of the most important process because in this one is where the agents interact. Here we can see the labor market, how is within the UT framework, and all the feedback loops that we have within those models. So here we can see in more detail how the job search and matching process works, and we can see that the wage model is a core element of that process. But in the Harmon thesis, he found out that the existing wage model is underestimating salaries, and this issue could be related with the way that the respondents provide information about the working hours. But also, we consider that this model is missing the random component of the wage distribution, because in the in the existing model, if two workers have the same attributes, those workers will have the same salary. But in reality, we know that two workers with the same attributes will have differences because one person has better negotiation skills, or simply because the other is more lucky to find a firm that can pay more money. So it will be interesting to introduce that random component in that model. So with that in mind, we wanted to build a model to predict salaries. So we wanted to move from point estimates, trying to think more about probability distributions. For that reason, we started thinking about the Bayesian approach. We investigate several data sources. We finally used the survey of labor and income dynamics, because this survey provides a very detailed information about the labor and income dynamics. And this was a survey, a program survey between 1996 and 2011. This survey was replaced by the labor force survey, that is a monthly survey. However, that labor force survey, the data that is available publicly doesn't have enough information to build this model. For that reason, we choose the SLEEP model, the SLEEP survey for this purpose. This is a national longitudinal survey. It consists on two panels of these household and respondents, and every individual was tracked for 6 years. This dataset was split in two sets. The first is the training set until 2007, and then we held out the validation set to measure the real performance of our model. Also, the monetary values in this dataset were converted to real terms using the consumer price index. So all values are in Canadian dollars of 2023. As we can see here, the distribution of salaries in the GTA area are positive and rise skew. So this is also something that we need to keep in mind if we want to model salaries. When we see some possible predictors based on the literature review, we can see that age, experience, tenure are positively correlated with salaries. But we can see that that relationship is a little bit weak. We have a high variance as we move to the right in those variables. Once we filter this data by, here I choose the one specific industry, public administration, we can see that that relationship becomes more clear. Still, we have that variance, but it's more clear, the relationship. So this is an evidence that, given the hierarchical structure, that if we introduce that structure in our modeling, we could get better results. So, in this case, we have three approaches to model salaries. We can have on the left side the pool model. In this model, we assume the data. There is no clustering in our data. We assume that there is no difference, and we can see that this model could have some problems with misspecification. Then we can say, well, we have some clusters, so we can estimate one model for each cluster. This give us better results, but we can see that the outliers here are affecting our analysis. On the other side, we have the hierarchical approach that sits between these two, and in this hierarchical approach, we model each cluster, but there is an information shared between those clusters. Assuming, for instance, when we are thinking about the tech industry, in the tech industry, most of the salaries in the tech industry could be higher because of the industry. So a secretary in the tech industry probably will earn more money than a secretary in another industry. The same for the CEOs, the same for the engineers. And in this approach, as we are sharing information, our model will shrink, that's the actual term, to the mean. So with this model is more robust to outliers, but also this shrinking effect help us to regularize our prediction. So we are reducing the risk of overfitting the noise in our data. So I'm not going to enter into the detail how Bayesian inference works, just to have a general knowledge. We have the prior knowledge. We define the shape and the parameters of this prior distribution, and we define one prior for each model parameter. We use our data to update our knowledge or priors and produce some posteriors. What we can do with those posteriors? We can draw some samples from those posteriors and generate several samples of our target variable, and we can build what we know as posterior predictive distribution. So when I refer to posteriors, I am referring to the distribution of the parameters. When I refer to the posterior predictive, I refer to the distribution of the target variable. So using that scheme, we can also apply to the no-pool model. In this model, as we previously see, so we define the priors, but for each cluster, so for each industry and for each occupation. And in the same way, these priors are updated, and we obtain some posteriors for each industry and for each occupation. And the hierarchical approach works in a similar way to the no-pool model, but in this case we define just the shape of the priors, not the parameters, and we define some additional distributions that are called the hyperpriors that define the location and the scale, the parameters of these priors. And this is the way that we share information between both levels. And then those priors are updated and we obtain the posteriors. In this case, the posteriors are similar to the no-pool model, but they encoded the information that we share in this part, in the hyperpriors. How this model looks, how the specification of this model looks like, this is just the hierarchical model. As you can see, in Bayesian statistics, we used a programming paradigm that is called probabilistic programming, in which all random variables are nodes, and the problem can be expressed as a graph. So we have the hyperpriors that define the parameters of our priors. Those priors are we calculate the linear combination of our priors with our dataset and calculate the parameter mu and the parameter beta, and those parameters enter the random component in this pi. And which is interesting, here we are modeling the systematic component as the linear combination of our predictors, and the random component is giving us the shape of our target variable. So once we run these three models, we can see, as we expected, that introducing the hierarchical structure, we obtain better results than the other structure. Here we are using the expected log point wise density measure. This is an indicator that is a proxy indicator that measures how much information we lost by using the distribution that we estimate instead of the true distribution. And the higher the better. It's a proxy measure of the KL divergence. Taking that in mind, that the hierarchical structure is the best, now we are interested in which variables are the most important. So we started with the most simple model, that is just having the intercept, that is the average salary by industry and by occupation, and we started adding some variables to that analysis. As we can see here, and as expected for the literature review, the experience, sex, education level are the most important predictors of salaries, while age and self-employment doesn't don't add much information to our analysis, so we can get rid of those variables, and our performance it won't reduce too much. Actually, that's better, because if we are also reducing the complexity of the model, we are reducing the risk of overfitting of data. So, the results here, in the results, we have to have in mind that this model will be, the idea of this model is that it will be used in a simulation approach. So we are also reviewing the results both at the aggregate and disaggregated level. So first, we can also perform some inferences using the parameters that we estimated. Here I just put some examples of the parameters. In the thesis there are the whole analysis of all examples, and I am focusing just on some specific industries and some specific occupations to use the analysis. So in this case, we can see that the parameters effect and variability is higher in the occupation side rather than in the industry. What we think about in this part is that the industry sets the average salary, the base salary, and the occupation captures the whole effect of the predictors. So, for instance, if we see here the effect of sex in industry is positive, but when we see the effect of sex in occupation is negative. But this value is higher than this one. So when we see overall the effect of there is a gender gap. The effect of sex in the salary is negative for females. And the same for experience. Experience is positive, so as we expected. Experience and education has, in general, in all industries and occupation, have a positive effect in the salaries. Then, in the prediction, so just a reminder, all of these calculations are performed using the validation set. So this set was not used in the model estimation, which provides the real model's predicted performance, that is also called out-of-sample performance. Here we can see our predictions of the salary distribution in the GTA area. We can see the same at the industry level. We can see that there are some industries that we are capturing the general behavior of the model, not the noise, which is good because we don't want to overfit our data. The same for occupation. And at the disaggregated level, as we wanted to include this model in a simulation framework, we have the red point is the salary, the observed salary, the salary that that person provided in the survey. The red distribution is the observed distribution of people with the same attributes. So if we compare those two variables, we can see that there are some workers that earns the expected value, while there are some other workers here that we can see they are some outliers. Probably they better negotiate or have or not. And with our prediction, what we wanted to do is capture the market value of that worker. So we can see that our prediction is closer to the observed salary distribution, and also includes in all cases the observed salary, the point estimate. So our conclusions. First, the introduction hierarchical structure allow us to capture those complex relationships in the data. This can be done manually by introducing some interaction terms. Actually, in the system model, there are some interaction terms, but the point is this process is performed manually. Instead, in this part, the hyperpriors that we defined, they are capturing and extracting that relationship from the data. The second part is that the definition of the gamma distribution as the random component of the model allow us to model that heterogeneity that we observe in the data and provide estimations. Also, we know that labor markets have some degrees of randomness, so we consider that the use of probability distribution instead of point estimates could help us to represent that, provide more realistic results. And finally, the Bayesian thinking is suitable for modeling complex systems. I really like the way that the Bayesian thinking process works, that we have some previous knowledge and we collect data and we update that previous knowledge using our data. Even we can use the outputs of these models can become the prior knowledge if we receive tomorrow additional data points for this work, we can include those data points very easily. I really like that way of thinking, but that comes with a cost, that is a computational cost. So, future work. First, unfortunately for time, we cannot run this model within the Harmon ABN framework. That will be a task to do in future work. But also, it will be really interesting to evaluate what other parts of that ABN model can be used or can be benefit from the use of Bayesian approach. Also, I think it will be really interesting to include job location as a predictor. What I read is that hierarchical models are especially good in spatial applications, and so it will be interesting to do that. Unfortunately, the data that we have available doesn't have that information, and this is another probably future work. If someone wants to work with this, I think from my research, I think that Statistics Canada has a lot of good data sets, but the only point is we need to apply it to the data center, so that process could take a little bit, but they have really good information that we can use in our models. And finally, we can include the model parameters covariance to improve the performance of the disaggregated level, to see more in detail these relationships between the predictors. This is very computationally expensive, but for now, because I'm totally sure that in a couple of years, this model will run half a time with the amount of progress that we are doing. And actually, a lot of research in the area, like in the samplers, or a lot of research also in a lot of breakthroughs in the chip industry will help us to make this approach more easy to apply. And I think that's on my presentation. I just have some acknowledgement. First, to my loves, Ale, Emi Avena, I will be nothing without your support. To Professor Eric Miller, thank you so much for your patience, your guidance, and your support during this journey. I also wanted to let you know that the CTS Complex Systems has been a course for me that changed the way that I see the world. And it's amazing how this course changed my perspective. Also, Colfuturo is a Colombian organization that provided the partial funding for my studies. Thank you, Professor Matthew Rorda, for kindly agreeing to read the thesis. I need to send you a thesis. And guys, to all of you, I learned a lot from you guys. Every chat, every talk that we had helped me to do this work, and I'm so happy to have shared those times with you. So